Hi, Wade Hampton students. Today we're going to be talking about Lewis structures a little bit more, and we're going to be focusing on a couple of additions to what we originally learned about making Lewis dot structures. And the first thing is we're going to focus on exceptions to the octet rule. Okay, now the octet rule is kind of the rule that says that while you're creating Lewis structures, you want to get 8 electrons around pretty much every atom in the structure. And this is due to the fact that we're trying to get the same number of valence electrons that stable noble gases have. Stable noble gases have 8 valence electrons. Probably the most important exception to that is hydrogen. Okay, so remember, hydrogen is stable with 2 electrons. And what this means is that whenever you see something connected to hydrogen in a Lewis dot model, there will never be anything besides just a single bond connected to hydrogen. So hydrogen is an element that only has one energy level. And remember that from your Bohr models, that first energy level only holds 2 valence electrons. And so if you have a bond, which is 2 electrons connected to a hydrogen, then that hydrogen is already satisfying that requirement and doesn't need any additional electrons. So you will never see dots on hydrogen. You will never see more than one bond connected to hydrogen. Hydrogen could never be in the middle of other atoms, because if you put hydrogen in the middle, it's connected to more than just 2 electrons. So you're never going to see anything like that, okay? Another interesting exception is beryllium. Beryllium is an element that can be stable with 4 electrons, valence electrons surrounding it. It's just and it's the only element that is like that. So an example of this would be something like beryllium difluoride, or BeF2, where the beryllium is in the middle of a couple of fluorine atoms, and the fluorine atoms have to follow the octet rule. And if you add up the total valence for this, there's enough electrons to get 6 dots on both of your fluorines, but the beryllium atom in the middle is stable with 4, and it's the only element that can be stable with 4, so that's an exception. Another exception that is less than 8 is boron. Boron can be stable in molecules with 6 electrons surrounding it. An example of that would be BF3. Okay. Boron can connect to 3 fluorine atoms, and in doing so, you see it's already got the 6 electrons surrounding that boron atom. And so, you might, while you're building this model, decide to make a double bond to one of these fluorines, but it really isn't necessary because boron is, or can be stable with only 6 electrons, and it is the only element that can be stable with 6. So these are exceptions. Most of the time we're following that octet rule. Now these exceptions are exceptions that are exceptions where you have less than 8 electrons. Let's look at some exceptions where you could go beyond 8, exceed the octet rule beyond 8 electrons. So basically, to go past 8 electrons, you have to have elements that have that 3rd energy level. You might remember from electron configurations, the first energy level only has 2 electrons. The second energy level, 2s2, 2p6, has 8 electrons. And when you get to the 3rd energy level, 3s2, 3p6, technically there's a 4s2 in here, but there is another part of the 3rd energy level that contains d electrons. And so you've got more than just 8 electrons in the 3rd energy level. And so elements that have at least 3 energy levels can technically go past 8 electrons when you're building them in Lewis dot structures. Now this usually only happens if they are the middle atom in the structure, and you have a scenario where you're connecting more than just 4 atoms to the middle atom. Okay, All right, so let's lay that out there and make a statement here. So any element with 3 or more energy levels can exceed the octet rule. And when I say, so how far can it go? Well, typically just due to, how many electrons you're cramming around the middle atom in the structure, pretty much for purposes of this class, you're only going to see the octet rule go past 8 for these elements, maybe to 10 electrons or possibly to 12 electrons, but that's it. That's as far as it's going to go. All right, so let's look at some examples of elements that might do this, okay? So some examples of that might be something like phosphorus. If you have like a PF5 molecule, the phosphorus atom that's in the middle will connect to 5 fluorine atoms on the outside here. If you add up the total valence for this, I think the total valence of your 5 plus your 5 sevens adds up to 40 electrons. And so that's just enough electrons to, fill up the octet for all of the fluorines that are on the outside. But you'll notice already, if you look just around the phosphorus atom here, I've got 1, 2, 3, 4, 5 bonds that each have 2 electrons in them. And so I've exceeded the octet rule to 10 electrons around that phosphorus atom. So that's what we mean when we say exceed the octet rule, okay? This is a case where, if you look around this middle atom in the structure, we've got 10, all right? Another example of that would be something like SF6, okay? Again, you're putting a sulfur in the middle and you're connecting it to all of the other atoms on the outside. This is a real molecule, sulfur hexafluoride. And I'm not going to bother putting in all the dots here, but you can already see if I connected that sulfur to 6 fluorines on the outside there, then it's going to have an octet rule that is exceeding 8. So the octet rule is being broken all the way to 12 electrons here. Yet another example of that would be a molecule like, say, xenon tetrachloride, or XeCl4, okay? If you add up the total valence for this, xenon has 8 electrons and each chlorine has 7, so we've got 4 sevens. 4 sevens is 28, plus 8 more adds up to 36 total electrons in the model. Okay, so you start building the model. You put xenon in the middle, and you connect it to 4 chlorines on the outside, and you've already used 2, 4, 6, 8 out of that 36, and then you can start adding in your electrons, so 8, 10, 12, 14, 16, 18, 20, and I'm trying to get 8 around every chlorine, 22, 24, 26, 28, 30, and 32. So right here, it looks like every chlorine is stable and the xenon is stable with 8, but I have 36 electrons in this model. And so I would have to put additional electrons in here somewhere. If you have additional electrons and you've got every atom filled up, and this is kind of rare, but when this happens, those additional electrons will go on that center atom if it has 3 or more energy levels, and xenon does. Xenon's in the 5th row of the periodic table, so it's got 5 energy levels. It has at least 3, so we need to put 4 more electrons in here. Now we don't want to connect them to other chlorines like with double bonds, because if we did that, we'd be breaking the octet rule for more atoms, and The gist is here we want to break the octet rule as little as we can, and so I'm just going to put a couple of extra pairs of dots on this xenon tetrachloride. Once you get into this kind of scenario, those extra electrons, if you were to run into any, probably are going to go on that middle atom in the structure. Okay? All right, so exceptions to the octet rule. Hydrogen, beryllium, and boron can have less than 8. And any element that's in the third row of the periodic table or below is going to have at least 3 energy levels and could possibly go to 10 or 12. Now, let me quickly talk about this just for a second. If there is a way to make an atom follow the octet rule for elements that have 3 or more energy levels, you should try to make it follow the rule first. Okay, so for these kinds of scenarios, try to make it follow the rule, but especially if you're connecting more than 4 atoms to that middle atom in the structure, you're going to have a really hard time doing that. Okay? All right, so now, the other thing that we probably need to add to what we've already learned about Lewis dot structures is a concept called resonance structures. Okay, so let's talk about a Lewis dot structure, for example, like sulfur dioxide. Okay, now if you were to build a model of this, you got your 6 plus oxygen also has 6, and another oxygen has 6, adds up to 18 electrons in the structure. And if you start to build the model for sulfur dioxide, put in your electrons, you're going to run out of electrons about right here. Here we've got to 18, okay? And you can see the oxygens are following the octet rule. I've got 8 electrons around each of those, but the sulfur only has 6 electrons surrounding it, so it's not stable yet. And we would need to move one of these pairs of electrons from one of the oxygens in to make a double bond, okay? All right, so let's suppose we take that pair and move it in to make a double bond to the sulfur. Okay, now we've got 18 electrons and every atom has 8. Okay, so this is a valid structure for sulfur dioxide. Now, someone else building this same molecule may have decided to take that double bond and place it on the other side of the molecule. And so then the question becomes, well, which model is right? And the answer is yes. Both models are correct, okay? If you look, one model is just I forgot my dots there. One model is just flipped over from the other one. And in reality, neither of these oxygens is any better at pulling on electrons than the other. Both of these bonds in reality are identical. If you, use some advanced techniques to measure the length of the bond and the energy of these bonds, you would find that the electrons are spending equal time between both of those. And so this kind of comes to a crux of what's good about Lewis dot structures and what's not so good about Lewis dot structures. So Lewis dot structures are fantastic for figuring out if valence electrons can be used to create stable molecules for atoms, and how those electrons would be shared versus not shared. Okay, we call these bonding pairs, and we call these lone pairs. Now, here's the bad news. Lewis dot structures put electrons in a specific location, and in reality, we know electrons are in constant random motion, and so, electrons from one side of the molecule can actually move completely to the other side of the molecule. These electrons are in constant random motion, and so, putting those electrons in a specific location is unrealistic. And so you could kind of think about one way to model this is that, well, if this model is good and this model is good, then maybe more in reality, this molecule is constantly flipping back and forth between these two structures. And so, if they're vibrating back and forth between these two structures, that's where the term resonance comes from. So these are resonance structures. Maybe one slightly more complicated model would be something where you had, a triple bond or 2 single bonds or a double bond and 2 single bonds. This double bond can move around to any of these other oxygens, and so you might end up with a scenario where you actually had, 3 different resonance structures for something like a nitrate molecule.